Swayam Prabha. Digital India. Educated India.
Welcome friends to this third lecture of week 7, and in this week we are talking about the redox chemistry of soils. In the previous two lectures we have talked about the basic concept of redox reaction and what is redox potential, and then we have talked about the redox potential and pH relationship. Also we have talked about the redox potential as well as PE relationship. Remember, PE is basically the negative logarithm of electron concentration, and this PE also indicates PE and EH are basically used simultaneously to denote the redox condition of a system, specifically in anoxic soil like submerged soils. And depending on the logarithm of the equilibrium constant and their PE values, we can define what should be the dominant oxidant species and what should be the reactant species available for this system. And also we have discussed the stability lines of different oxidized and reduced species couples, and based on that we have seen at which condition which form will be more dominant. For example, we have seen that the iron line, that is Fe3 Fe2 plus line, is basically the border line between this axic and anoxic system, and whatever species which are present above this line tries to remain in the oxidized form, although their thermodynamic equilibrium is tends towards reduction, and vice versa for those species which are present below this line, just like the sulfide. So, and also we have discussed what is the implication of these high PE values and low PE values and these lines, and we have seen that the manganese oxide, which has higher PE values than the arsenic 3 and arsenic 5 and plutonium and other species, they can oxidize those species by getting itself reduced, this manganese oxide, because of the higher PE values. Now, in this lecture we will be talking about calculation, how to calculate the log of K0 and PE, what is their actual relationship, and then we will be trying to discuss the actual chemistry of submerged soils, and also I will try to discuss the practical implication of these EH values as far as the soil chemistry is concerned. So, let us start with this calculation of logarithm of equilibrium constant and the pH. Now, we have seen that the half reaction below basically shows the reduction of Fe3 to Fe2 plus. You can see FeOH2 plus electron plus 1 proton, we get Fe2 plus H2. So, basically from plus 3 we are getting plus 2. So, it is basically reduction from Fe3 to Fe2 plus, ferric form to ferrous form. Now, in this reaction there is one electron transfer, as you can see, from plus 3 to plus 2. So, n equal to 1. So, if you remember our previous equation of equation 8. So, for your convenience, let us go back and see what was equation 8. So, if we go back, so our equation 8 was K0 equal to concentration of reduced species over concentration of oxidized species multiplied by e to the power or electron to the concentration to the power n, and H plus or proton concentration to the power n. So, here this electron is 1, and if we consider this, Then, so in this reaction, if we put the E value of E equal to 1, then ultimately and also consumption of one proton. So, electron of one transfer of one electron means consumption of one proton. So, here m equal to 1. So, basically Fe3 plus and Fe2 plus is an imposed condition. If we consider this is an imposed condition, the concentration of ferric equal to the concentration FeV2 plus, then this whole equation will turn into this equation, that is equation 10. Now, equation 10 says P equal to then this is a logarithmic term minus m by n pH. We know that this is equation 10. This whole thing will be reduced to this P plus pH equal to log of K0. We also seen that in our previous lecture. Now, at pH 0 we also know that P equal to log of K0, and relating this natural logarithm of K0 to this Gibbs free energy, we can get this equation. So, all these things we have discussed in our previous lecture. So, now what is new? Now, we know that the Gibbs free energy of the whole reaction is basically the difference between the Gibbs free energy of products and Gibbs free energy, summation of the Gibbs free energy of the reactants. Now, if we solve these reactions, so if we put these values of the free energy of these products and free energy of the reactants, we will get this value, that is minus 87.01 kilojoule per mole. Now, using this equation 14, we can see that minus delta G0 R by 5.71 equal to log K. We have seen that also in our previous lecture. So, now we know the value of delta G0 is equal to 87.01. So, basically it will be 87.01 by 5.71. So, that will be value of 15.2. So, for this half reduction reaction from Fe3 to Fe2 plus, we have calculated the value of log K0 equal to 15.2. How we have calculated again? We have seen we have calculated based on the free energy, calculating the free energy, and once we calculated the free energy, we are basically inputting that value into the equation 14, which you have already seen previously. Now, we have calculated is 15.2. Now, this value for log K0 is the same as we have seen in our table for the reaction of equation 1. So, you can see in this table this FeOH whole 2 to Fe2 plus. So, Fe3, that for this reaction we know that the log K value was 15.2. So, this value of log K0 is one shown already we have seen in the table for this reaction in equation 1. Once you calculate the P at pH 5 and 7, one would use the equation 11. So, what do we know from the equation 11? Equation 11 we know that P plus pH equal to log of K0. From there we have seen that at pH 0, P will be equal to logarithm of K0 or equilibrium constant. So, this is the mother reaction. This is basically the original relationship P plus pH equal to log of K0. Now, for pH 5, substituting the value of 15.2. So, we know the value of log K0 equal to 15.2 and pH 5. So, we get a value of P of 10.2, and for pH 7 similarly inputting the values, we are getting the value of 8.2. So, we can see, we can verify these values with the table which you have seen 15.2, 10.2 and 8.2. So, this is how we calculate the value of log of K0 as well as the P at different pH levels. So, basically we have to use two different formulas. One is for the Gibbs free energy. If we input the Gibbs free energy for that reaction, we will calculate the reaction Gibbs free energy. The reaction Gibbs free energy can be input to get the value of log of K0, and from there if we input the value of log K0 into P, pH and log K0 relationship for different pH, we will get this value of P, and then we can verify these values. Now, another very important term we generally come across when we discuss the submerged soils is called the poise. Now, the poise of a redox system is the resistance to change in redox potential when the addition of small amounts of oxidant or reductant. Again, the poise of a redox system is the resistance. So, it is a kind of a buffer. So, it is basically resistant to change in redox potential with the addition of small amount of oxidant or reductant. So, when you add oxidant, it slows down the poise, basically try to to counterbalance the change which is basically initiated by these oxidized oxidant and vice versa for the reductant. Now, poise increases with the total concentration of the oxidant plus reductant, and for a fixed total concentration it reaches a maximum when the ratio of oxidant to reductant is 1. Okay. So, this is called poise. It is basically a resistant or buffer which basically acts to resist the change in redox potential when we are adding a particular small amount of oxidant and reductant, and its value becomes maximum when the ratio of oxidant to reductant is 1. Now, what is the measurement and use of redox potential? So, generally in case of soil, the measurement of redox potential is usually done with platinum electrode, and the electrode will transfer the electron to or from the medium, but it should not react with the medium. Remember that once the platinum electrode is combined with the half cell of the known potential, now reducing system will transfer electron to the electrode. However, vice versa, in case of oxidized system, it will remove electron from the electrode. So, redox measurements are most reliable for flooded soil and sediment. I have already told you in our previous lecture that although we talk about oxidation potential or in case of different chemical reaction, however, in case of soil, for example, in case of flooded soils and sediments, we more talk about the reduction potential. Now, oxidized soils generally have a redox potential of plus 400 to plus 700 millivolt. Okay. In case of oxidized soils, in case of oxic soils, you see that, or in case of aerobic condition, you will see the redox potential generally vary from plus 400 to plus 700 millivolt. And in case of seasonally saturated soils, they have a redox potential of plus 400 to again plus 700 millivolt in case of oxidized system to highly reduced system, which varies from minus 250 to minus 300 millivolts. So, you can see that in case of oxidized system, the redox potential generally is positive, ranges between plus 400 to 700 millivolt. In case of anoxic, in case of seasonally saturated soil, when it is in aerobic condition, it again it shows the same 400 to 700 millivolt. However, in case of reduced condition, when all the pore space are filled by water, then you can see then it is highly reduced and showing the redox potential of minus 250 to minus 300 millivolt. Now, what is the implication of EH? Now, if the redox potential data are combined with other information such as depth to the water table and oxygen content of the soil, it basically helps to know the wetness of an environment. Obviously, this redox potential is more highly used in case of defining the condition of an anoxic soil, or in other words the chemical dynamics or chemical condition or chemical condition of a flooded soil or submerged soils. So, basically the wetness of an environment can be detected by using these EH values with the help of some other indicators. Now, wetland sites that have low redox potential have had long period of flooding and soil saturation. So, obviously, the wetland soils which are all the time which are saturated with the water for long time, they have a tendency to produce the very low redox potential. And remember that redox data are also useful to understand the morphology and genesis of the soil. Obviously, a particular type of soil, when it is developed under the waterlogged condition, we will see that in case of submerged soil what type of morphological features we can see. We can see the bluish coloration, we can see mottling. So, these type of features, these type of color features are very prevalent in case of waterlogged soils. So, the redox data are also useful to understand the morphology and genesis of the soil. So, if you see the redox data of that soil, we can identify, okay, this environment may have created this type of soil. So, soils that undergo alternate oxidation and reduction cycles are usually mottled. We will see that picture in a while. So, basically an alternate oxidation reduction in case of soil basically changes their color, we call it mottling. So, these soils are these mottled soils are very much prevalent in case of these alternating wet and dry cycle, wet and dry these mottled colored soils are basically found in case of these soils which are which undergo this seasonal oxidation and reduction. Now, the different redox conditions will of course not only affect the chemical status of the plant nutrient, but also the activity of the various microorganisms. Now, because soil organisms are composed of approximately 90% of water, their redox activities are expected to be confined within the borders of the stability of the water. So, obviously, not only the soil chemical reaction, but also biological activities also being controlled by this redox potential. Now, these organisms which are present in the soil do not oxidize directly, but acts as a redox catalysts, and basically they mediate the oxidation of substance or the reduction of oxygen. Now, sulfate reducing bacteria, just for an example, let us talk about sulfate reducing bacteria. So, sulfate reducing bacteria mediate the reduction reaction from sulfate to sulfide, become active only when the EH decreases below 0 millivolt. So, unless the EH of that system goes below 0 millivolt, this sulfate reducing bacteria will not be effective, and once it is effective, it will then change the oxidized form, that is sulfate, to reduced form, that is sulfide, which you have already seen. Now, in general, aerobic soil organisms thrive in normal or oxic soils, whereas where the drainage is excellent, that is obviously that means low electron activity. When the drainage is excellent, that means more oxygen means less electron activity, that means less electron activity means there will be aerobic conditions of soil organisms, the aerobic soil organisms will grow in that condition. An anaerobic organism flourished in waterlogged condition, where all the oxygen are basically exhausted by they have been replaced by the water. Also, so these organisms basically flourish in waterlogged condition. These anaerobic organisms which do not require any oxygen for their growth. So, they flourish in the waterlogged or anoxic soil where the drainage is poor, there is high electron activity. Now, wet or suboxic soil, that is medium electron activity, may contain facultative anaerobes organisms or a mixture of aerobic and anaerobic microorganisms. Facultative anaerobes means those which are inherently so facultative anaerobe means those organisms which can thrive in both aerobic and anaerobic conditions. So, this is called the facultative anaerobes. Okay. So, these facultative anaerobes will survive in this wet or suboxic soil. Okay. And basically a mixture of aerobic and aerobic, basically they showed mixture of aerobic and anaerobic organisms, and most predominantly the facultative anaerobic organisms. Another implication for this EH in the soil can be illustrated using this graph. You can see here. So, this basically shows an illustration of the variation in redox potential when reduced iron is oxidized by an oxidizing agent. So, suppose this reduced iron, that is Fe2 plus, is oxidized to Fe3 plus by some oxidizing agent. Now, you see if we plot the percentage of Fe3 plus present in the x axis and millivolts or EH in the y axis, then you will see a curve like this. So, this curve in the figure indicates that oxidation of Fe2 plus causes the redox potential to rise. So, you can see when the concentration of Fe3 plus is increasing, that means conversion from Fe2 plus to Fe3 plus is increasing. As a result, there is also increase in redox potential, as you can see it is increasing. Now when 50% of Fe2 plus is produced and present, the redox potential equals to 770 millivolt. So, we can see here at 50%, when the 50% of Fe3 is produced and present, the corresponding redox potential is around 770 millivolt. So, this can be verified statistically by assuming that the half cell of reaction is basically this, and it is characterized by a standard potential of E0 770 millivolt. Now, we have seen the redox potential for this reaction was formulated as that EH equal to E0 0.059 log of concentration of Fe3 by Fe2 plus. So, we know that here Fe2 plus Fe3 plus 50% we have seen here. So, here by putting these values into this reaction, we will see EH equal to E0 plus 0.059 log of 1. So, from there we can see a value of EH equal to E0 equal to 0.770 volt. So, these reactions, this simplification can be done from this graph. Now, what are the other implications of EH? Now, drastic changes takes place in the physical, chemical and biological condition of soils with development of poor aeration and waterlogged condition. Obviously, when there is a poor aeration and waterlogged condition, there is drastic changes in physical, chemical and biological condition, because chemical reaction will be there because of absence of oxygen, and also biological organisms will not be the composition of biological organisms will change depending on the aeration status. Now, oxygen content decrease rapidly in poorly aerated soil. So, when the soil is poorly aerated, the oxygen content will decrease rapidly, and the respiration of plant roots and microorganisms will rapidly consume the remaining oxygen in the soil. Obviously, when an oxic soil become anoxic or become waterlogged, the oxygen which is trapped inside the pores are easily or very rapidly utilized by the aerobic microorganisms which are present in the soil or by plant roots. So, therefore, oxygen content decreases with a decrease in EH, obviously. So, at these low EH values, the dissolved oxygen in the soil water will be used by the microorganisms, and at very low EH values, even the combined oxygen in the form of ferric oxides, nitrates and sulfates will be attacked. So, basically, when there will be no oxygen present at highly reduced condition, these nitrates, sulfates will be used as a terminal electron acceptor by the microorganisms for their survival. So, because they do not have the oxygen over there. Okay. So, this is how these these changes of this redox potential shows a profound influence in the chemical, biological and physical properties of the soil. Now, a notable chemical effect resulting from waterlogging is the conversion of insoluble iron and manganese oxide into soluble Fe2 plus and Mn2 plus. Okay. Now, we generally see that when there is a waterlogging, the Fe2O3 or ferric oxide will reduce to Fe2 plus by taking 2 electrons, and then manganese oxide MnO2 is basically converted to Mn2 plus. So, it is reduced. So, both Fe2 plus and Mn2 plus are formed, and these Fe3 form and Mn3 forms are basically insoluble in nature, and when they convert into Fe2 plus, and that means when they convert from manganic to manganous and ferric to ferrous, they will be converted from insoluble form to more soluble form. So, consequently, in those poorly aerated soil in which the reduction process prevails, iron is found as Fe2 plus and manganese is found as manganese and nitrogen will be found as ammonium and sulfur will be found as sulphite iron. On the other hand, these iron are present in the oxidized states in well drained soil, like just like in the oxidized state they will be present at Fe3, Mn4, then nitrate and sulphate. So, basically these are some of the very important element which shows a profound influence of EH in their conversion in the waterlogged soils, and as a result their availability to the plant also changes. Remember, when they become more soluble, the plant can absorb them through their roots. So, again in the aerobic condition, these iron will be present as Fe3 plus form, manganese will be present as manganic form Mn4 plus, nitrogen will be present as oxidized nitrate form and sulfur will be present as sulphate form. However, in the reduced condition, when the EH is very low, then the iron will be present as Fe2 plus form, manganese will be present as Mn2 plus form and nitrogen will be present as anaerobic NH4 or ammonium form and sulfur will be present as sulphite form. So, biologically decreasing oxygen contained in soil produce drastic changes in the population of soil microorganisms, we have discussed it. Now, at low oxygen content, anaerobic microorganisms like some actinomycetes species may prevail over aerobic microorganisms. Now, these EH also not only they have application in soil, but also they have application in other disciplines also. For example, in medicine, the redox potential is applied for the detection of certain diseases, and low values of the redox potential basically values of redox potential around the gum increase the risk of gingivitis, which is a gum disease. So, you can see this redox potential not only controls different soil reaction, but also it has application in other sectors also. Now, let us start a very important chapter, that is submerged soils. Now, submerged soils are the soils which are submerged in water for a sufficient period of time to give the distinct horizon development differentiating from other soils are known as submerged soils. And the submerged materials basically influence the type of soil which develop from it, the type of aquatic life and crops it supports, and capacity of these sediments to access a sink for terrestrial wastes. Now, this submerged soil can be, they have different types of, we have different types of submerged soils. One of the important submerged soils is paddy field or rice fields. Another type of submerged soil is wetlands. So, these wetlands, these submerged soils have their typical chemical dynamics, and we can see different types of features or properties of these soils, not only their chemical nature, but also their physical appearance. So, based on that, these submerged material basically influence the type of soil which develops, and also type of aquatic life, and also the capacity of these sediments to sink for terrestrial waste. So, guys, let us wrap up our lecture here, and in the next lecture we will be talking more about these submerged soils, and we will see what are the other properties of the submerged soils. Thank you very much.